Hi, welcome back to our tutorial on the calculation of internal forces. This is gonna be the second video on this series. And yeah, last time we already introduced the different internal forces that we have. That means normal forces that basically tell us if the rod or the beam is under compression or tension. For shear forces, we explained that we're going to use a little trick here. We're going to look at the beam from the right side to the left, okay? And each time that we have a single force, we're just going to input a jump in the shear force distribution. And for the bending moment, we're going to try to picture how the beam or how the system is going to deform. And on the tensile side of the column or the beam or the rod, the bending moment is going to be there. Okay, the bending moment is going to be on the tensile side. So when a system, when a beam is deflected, it has a specific curvature. We explain what's going to be a positive curvature, what's going to be a negative curvature, so that we can know on which side, what's going to be the sign of the moment, kind of. So let's start. We should do the level 1 and level 2. I'm going to explain what's happening. So here we have a normal beam. On the left side, a pin support. On the right side, a roller support, okay, or sliding support. And what is the loading here? The loading here is a single moment. So what does that mean? In this beam, we're only gonna have bending moments, okay? This beam is neither compressed nor stretched. That means that for the normal forces, it's zero. Nothing's going to happen there. Now, what happens here? We have a vertical loading. Okay, it's a linear loading, but it doesn't matter. It's a vertical loading. So our supports are going to have reaction forces upwards. But if we do some of the forces in the horizontal direction, we see that there's no loading here in the horizontal direction. The right support, the roller support, can't take any loads in the horizontal direction anyway. Now, the left support, the pin support, can take forces in the horizontal direction, but it's going to be the only horizontal force in the horizontal direction here. So when we do some of the force in the horizontal direction, it's going to be zero. That force is going to be zero. So now shear force is very good. So we use our trick again. We start reading the beam from the right side, not from the left. On the left side, we have a clamped support with 3 reaction forces. On the right side, we have a free end. So we look at the beam from the free end towards the clamped support. What happens? At the free end first, we have something like, let's say we don't even have the load yet, because this is a distributed load. It's going to increase linearly. Okay, first it's 0, and then we go downwards in the direction of the load. Okay, so the right one is 1, this one is right, yeah, 0, and then downwards in the direction of the load, so going downwards and then with a linear increase. What we have here, the same system as earlier, but now we have a single load there. That single load has some inclination, okay, so we can actually part this load into 2 different directions, a vertical one and the horizontal one. How will be the horizontal one? The horizontal one would be directed to the left, from the right to the left. So it's going to put the beam under compression. And we say that compression for a beam is a negative moment, so not on the side of the line, but upward. This one is right. Yeah, moment. Very good. How is this system going to deform? Look, on the left side, we have a clamped support. That means that point down the left can't move at all. On the right side, we have a free end. That means that that point on the end, that node, is going to move downwards. And now you can picture yourself how the system is going to deform, okay? We're going to have a so-called positive curvature, what I explained in the first video, or if you want, the tensile side is going to be upwards. So the moment is this one. Now the distribution, the way it was distributed, the formula, I mean the function, was due to the fact that the loading was a constant load, so it's like quadratic moment. So here, shear forces. But what do we have as a loading? We have a single moment. Okay, that single moment is gonna go directly in the clamp support. The clamp support is the only support here, the only support that's even here that can take that moment. So in this beam, we only have a normal moment distribution, but no shear forces. Okay, when we look at the beam from the right to the left, there's no force there. Okay, a single moment is not a force in itself. It's not a force. It's a moment first. Okay, yeah. Two forces can create a moment. Yeah, that's true. Even a single force can create a moment in the bending distribution, but there we didn't have a force to make a jump or something. So shear forces, again, we look at the beam from the right to the left. That's our trick, right? On the right we have a roller support, on the left we have a pin support. The loading is a constant distributed load. Okay, that means our shear force is going to be linear. It's going to go from the right to the left. It's going to go downwards linearly. So it's only going to be, it can only be this one here. Why did we have a jump on the right side? Because of the reaction forces of the supports. But we only need to know to solve that problem to know that it's going to be linear going downwards, and that was it. So shear forces again. Look, the left element there from the hinge to the pin support, it's a so-called rod. Why? It's linear. It doesn't have any angle in it. It doesn't have any loading perpendicular to it except at the hinge, and it doesn't have any single moment. So it's a rod. It can't have a shear force. Okay, on the tree. So the right one here is wrong. For sure, this one right, because when we read the beam, when we read the beam from the right to the left, we could see that at the hinge, we need to have a jump downwards because of that load. That's why that middle one was right. Okay, now this one, what do we do here? At the right end, we have a single moment. That means we need a jump. Oh, I need to stop this first. Fuck. Okay, we need a jump there at the right end, and then it's gonna be constant and move downwards. This one is right, so I didn't explain that one correctly because of the core was disturbed a little bit. Here, the left part from the hinge to the left is a rod. Like, it can't have shear forces or bending moment. So the right solution can only be one of those two here. Now, on the right, on the pin support, it's kind of like a range. So the moment there should be 0. That's why this right answer here can be right, also can be the correct one. The only correct answer can be this one here in the middle. Okay, we're almost there. So what's gonna happen here at the top? We're gonna have a jump in the moment distribution. Okay, at both supports on the left and the right, the moment distribution should be 0. So that being said, this right answer could be the right one. This one could also be the right one. This one can't. Why? Because the moment distribution is staying on the same side. We don't have any jump in this answer. Now, how do we know which one is right? I think I'm going to do a video explicitly on those single moments to explain that. The right answer is this one here. It's going to be a little bit difficult here with the time constraint. We had this system before, and I said that the left element from the hinge to the pin support was a rod, meaning that it couldn't have any shear forces or any bending moment. I also explained why, and one of the reasons was that we didn't have any loaded perpendicular to that rod at the moment, but now we do. Okay, so it's not a rod anymore. It can have shear forces, it can have bending moments now. Now, how the bending moment left should be 0, at the hinge should be 0 again. So this one in the middle is wrong. This one is possible. It's this one that's right. Oh, I wasn't even fast enough to solve it. Okay, because of all the explanation, but we were basically there. That was the end. You see, it's like 6 over 6 was the last one, and then we will go to level 3. So no, I don't consider that I failed this. And since we can see, okay, you can also see the explanation is actually good, that that I didn't do this fast enough, because you can see that when you missed, you get some explanation of what happened. This is exactly what I explained, that the range here should be, the moment there should be 0. And why is this distribute? Okay, they also said it. Okay, that's the reason why I didn't pick it, because the moment distribution here is quadratic. At least it's like you have a parabolic form. But if you look at the system over there, we don't have, on the right side, we don't have any loading, we don't have any distributed load, so the moment should be linear. Okay, that's why we don't take that right one, and that's why the left one here was correct. I just didn't have enough time to press it. When I pressed it, the time was over already. So that's the thing. I always need to look out for how much I explain here, so that we can still move forward. Yeah, that was it. Thanks for your attention, and see you next time.